Hello Vulkan developers! One of the relatively recent additions to the Vulkan specification is dynamic rendering. In a nutshell, it allows us to conveniently get rid of both the render pass and the frame buffer objects and allow greater flexibility when setting up the render target. This feature was introduced as an extension and became a core part of Vulkan starting from version 1.3. As you've probably seen in one of my short videos, I'm using the 3D Graphics Rendering Cookbook as a guide for this series. Unfortunately, this book was published mid-2021, while dynamic rendering came out later that same year. Therefore, the book relies exclusively on the older mechanism of render passes and frame buffers. Fortunately, a new edition was published this year, 2025, so of course I went ahead and got it. Notice that they changed the title a bit. Previously it was a guide on both OpenGL and Vulkan, and now it is only on Vulkan. So right now I'm slowly transitioning between books, and it seems that dynamic rendering is a good place to intercept the new edition. Before we get started, I'd like to say a big thank you to Evgeny, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev, or by joining the YouTube channel as a member. To enable dynamic rendering, we need to make sure that the system, as well as the device, support it. And by saying system, I mean mostly the Vulkan instance. So we start by checking the Vulkan version that the system supports, and we do that even before the instance is created. Okay, so we go to the Vulkan core class, to the create instance function, and I've added a function here called getInstanceVersion, which is defined up here. And to get a version, we call the Vulkan API vk_enumerate_instance_version. Not sure why they call it enumerate and not get, because we're not really enumerating anything here. But anyway, what we need to do is to provide the address of a 32-bit unsigned integer, which is defined here. And then the major, minor, and patch level are encoded in those bits. But we don't really need to know where they start and end in terms of the bits, because the Vulkan SDK provides us with these convenient macros, VK API version major, minor, and patch. They take the instance version and return the corresponding value. So if you're interested, you can take a look at the definition of the macros, and then you'll see exactly where the bits are, but we don't really need to care about this right now. So to save the version, I've added a structure called mInstanceVersion in the private section of the class of the Vulkan core, which contains the major, minor, and patch level. Back to the createInstance function, now that we have the version, we can go ahead and create the instance, as usual, by calling vk createInstance, and we have the instance createInfo structure here, which contains a pointer to the app info. And then this structure contains an API version of Vulkan. So the idea is that we can basically create a Vulkan instance of different versions, and this will work as long as these versions are actually supported in the system. So if you remember, in the first video in this series, I created a Vulkan instance of version, I believe it was 1.1, if I remember correctly, which is kind of like the minimum, and will probably work on all systems, but for dynamic rendering we need at least 1.2. So what we do here is that we get the version from the system, and then we create an instance of this version. So to do that, we use the macro vk_make_API_version, which takes 4 parameters. Okay, the first one is variant, and right now it is 0, and then the major and minor and patch level. So the major and minor versions come from the instance version variable, which we've just updated, and the patch level is 0. And the reason for that is that we don't really care about the patch level, we just need 1.2. Any patch level should work. The next step is to get the extensions that are supported by the physical device. So if you remember, we have a class called Vulkan Physical Devices, which maintains information about all the devices in the system. It is also part of the Vulkan core, and we've covered it in one of the first videos in the series. So this guy has a vector of a physical device, which is a big structure with all the information about the physical device, such as device properties and stuff like that. And what I did here for this tutorial is to add a vector of VK extension properties. And this structure contains the extension name, which is simply an array of characters. The maximum extension name is 256. And we also have some version here. So now we need to populate this vector. So we go to the init function, and we have this loop here over all the physical devices. And I've added a function here called getExtensions, which takes the index of the current physical device. And what we do here is to call the Vulkan API enumerate device extension properties twice. First, we need to get the number of extensions. And once we have that, we can resize the vector of extensions. Okay, dev is simply a reference to the current device in the mDevices vector. So the first call to this function takes the physical device handle. The second parameter is a layer name, but we're not limiting this call to a certain layer, so we just use a null here, and then the address of the extension count, and the null at the end. And now that the vector has been resized according to the number of extensions, we call the function again, and then the last parameter contains an address for the result, which is simply the starting address of this vector, of the extension vector. And then optionally, if you want to print out the extensions, then you can simply do a printf or cout on the extension name member in the extension properties structure. Now, if we go back to the init function in the Vulkan core, we've created the instance and we initializes the list of physical devices. So now when we create the logical device, we can try to enable dynamic rendering. Now there are a few options here. If we know that the version of the Vulkan instance is 1.3 or more, then basically we don't need to do anything because we know that dynamic rendering is part of the core specification at this version. But if the version is 1.2, then we need to explicitly check whether the device supports dynamic rendering through the extension. And that's what we do in this piece of code that I've added here before the creation of the logical device. First, we have this variable that says device supports dynamic rendering, which is initialized by going to the list of physical devices, calling selected returns the physical device which was selected for rendering. And then I have this new function here, isExtensionSupported, which takes the name of the extension. Now this guy, vkkchart dynamic rendering extension name, is a macro which is defined to be the name of the extension. And since it is defined by the Vulkan SDK, it's probably better to use it than trying to enter the string yourself and sometimes make a typo here. As I said, isExtensionSupported is a new function in the physical device structure. Okay, we've seen this new vector of extensions. So this function takes a string of an extension and returns a Boolean value. And all it does is to traverse the list of extensions. It creates a C++ string from the requested extension as well as from the current one in this iteration, and then it compares it and returns true or false based on whether the extension was found. So now we know whether the device supports dynamic rendering through the extension. Next, we check whether the instance is 1.3 or more. So we check whether the major version is greater than 1. Right now we are at version 1.4 of Vulkan, but in the future, I assume there will be versions such as 2, 3 or more, and then they will probably include dynamic rendering. And if this feature is ever deprecated, then of course we need to take care of it, but right now let's assume that it will be present in the future. But if the major version is 1, then we check whether the minor version is 3 or more. Next, we check whether those two Boolean flags are true. Now this check may be a bit redundant, but I decided to include it anyway as a precaution. I don't know if there is a case out there where the instance version is 1.3 or more, and then the extension is missing. It seems to go against the rules, so you can decide for yourself whether you want to include this check. If one of these two flags turns out to be false, then we check whether the minor version is 2. And then we check whether the device supports dynamic rendering. So this is the case of version 1.2. We check the device, and if the extension is supported, we push it into the vector of extensions. Okay, dev extensions is defined up here. Right now it just includes the swap chain and the shaded draw parameters. So in this case, we will add the same extension that we checked here. But if we are at version 1.2 and the device doesn't support the extension, then we print an error message and we exit. And the same goes for the last check here, which we will get to if this version is prior to 1.2, so like 1.1 or 1.0. So I think that the most important thing in this entire piece of code is knowing when to push the extension into the list of extensions that you're going to explicitly request. Because if this is version 1.2, then you have to do it. And then all the other checks are kind of like my own preference for this tutorial, but they may not be generic enough. Next, we define a structure of the physical device dynamic rendering features KHR type. We specify the type of the structure, null for the next pointer, and then we set dynamic rendering to be true. And then in the device create info structure, we set the pointer next to be the address of this new structure. Okay, so this one existed in all the previous tutorials, or at least starting from the one on the creation of the logical device. And this is a new addition of this tutorial. So this kind of weird feature of Vulkan allows you to chain together lists of creation device or features of the device. So if this is not a null, then the system will go to this address. It will detect the type of the structure because it always starts with some magic number. And then it probably casts the pointer based on this type and checks the remaining attributes. So the idea is that when we get to this point in the code, then we know the dynamic rendering is available, so we simply request it like that, using the pointer, the next pointer. And we can see the use of the vector of extensions right here. And that's it in terms of creating a device with support for dynamic rendering. Next, we have a few changes in the graphics pipeline object, where we also need to specify some definition of dynamic rendering. And as you can see, we are in the graphics pipeline v2 class, which was introduced in the previous tutorial. So I've made all the required changes here and didn't touch the old version, because that one exists only for backward compatibility with the older tutorials. But there is also some backward compatibility with this class here, because it still takes the render pass as a parameter in the constructor, but we will not use it today, as you shall see in a minute. We do have a couple of new parameters here, the color format and the depth format, and we will see later on how to retrieve them. So we pass them on to the init common function, and then when we call create graphics pipelines, we provide the address of the pipeline info structure, which is here, and to set the pointer next, we check whether a handle of a render pass was provided. If it was provided, then we set the next pointer to be null, and then the render pass also goes into its own attribute. Okay, so this is the old behavior of the code. Previously, there was simply just a null here, and not this check. But now, if the render pass is in fact a null, then we set the pointer next to be the address of a new structure called rendering info. And then, of course, if render pass is null, then it will be a null here as well. So there's no problem here. And the rendering info structure is defined up here. And what it does is basically replace some of the functionality which was provided by the render pass. So if we jump to the Vulkan core for a second, to the create simple render pass function, we can see that it included a description of the color attachment, the depth attachment, subpass. So the pipeline rendering create info structure replaces some of this stuff, specifically the formats. So we need to specify the number of color attachments, which is 1 in our case, and then a list of the formats of the color attachments, the format of the depth attachment, and the format of the stencil attachment. And since we have a single color attachment, we can simply set the address of the color attachments to be the address of this new parameter color format. We also set the depth format, and the stencil attachment is format undefined. Okay, so basically this check here allows this class to be backward compatible with the previous tutorial. But if you want to remove this backward compatibility, then of course you can simply drop this parameter here. And finally, we have a few changes in the application code. So I'm going to go over them by comparing the old version here on the left and the new one on the right. So first of all, we can see that in the private section of the class, I removed the handle of the render pass as well as the vector of frame buffers. Okay, because we don't need them when we use dynamic rendering. So their creation and destruction was removed from the init function and the destructor of the Vulkan app. Next, we have the creation of the graphics pipeline. So in the old tutorial, when we allocate the graphics pipeline object, we provided the handle of the render pass, and now we have a null here, and we need to provide the color format and the depth format in the last two parameters. So I actually copied this piece of code back to the old tutorial for forward compatibility, but you can also use VK format undefined here, and it will work in the same way for the old tutorial. Now these two functions, getSwapChainFormat and getDepthFormat, are actually new in the Vulkan core class, and so getSwapChainFormat goes to the SwapChainSurfaceFormat attribute, which was saved in the class back when we created the swap chain. This structure contains both the format and the color space, but here we only need the format, so this is what we return. And for the depth format, we go to the list of physical devices, to the selected physical device, and it also contains an attribute called depth format, which I believe was added when we implemented support for depth buffering. And now the pipeline is created with support for dynamic rendering, and then most of the remaining changes are in the record command buffers function. As you can see, I removed the initialization of the render pass begin info structure. We don't need that. This line was also dropped. It updates the same structure. And then we don't need CMD begin render pass, as well as CMD end render pass. Instead, we have a couple of barriers here, and then a new private function of the class called begin rendering, and then CMD end rendering. Okay, so this one was CMD end render pass, and this one is CMD end rendering. So make sure to use the correct one. Now let's jump into Visual Studio and take a closer look at these changes. First, we have the two barriers before we begin rendering, and then after we end rendering. And the reason is that one of the conveniences of the render pass is that it handles format transitions for us. But now that the render pass is gone, we need to do it ourselves. So after we begin the command buffer, and just before we end the command buffer, we have two barriers. The first one will transition the layout from undefined to color attachment optimal, which is the required format of the color attachment when we plan to render into it. And then after we end the rendering, we transition from color attachment optimal to layout present. And then the system can present the image. The function ImageMemBarrier also takes the command buffer handle, the image, and since we're traversing all the command buffers, we have one command buffer per swap chain image, we get the corresponding image from the Vulkan core. We also need a swap chain format, and we just saw this function. We've already seen this function in a previous tutorial. As I said, I copied it from the 3D graphics rendering cookbook, but I had to add support for the new transitions. So most of the code in this function simply checks the old layout and the new layout, and then sets the source axis mask and the stages, source and destination. So I've added a couple of checks at the end. If we are transitioning from undefined to color attachment optimal, then the source axis mask is 0 and the destination axis mask is color attachment right bit. Because of course we are rendering into the color attachment. The source stage is the top of the pipe, which matches the undefined layout at this point. And then the destination stage is color attachment output. So this takes care of the first transition, and then the second transition is from color attachment optimal to layout present. And then everything is reversed. The destination axis mask, which was color attachment right, is now the source axis mask, and the destination axis mask is 0. The source stage is now color attachment output, and the destination is the bottom of the pipe. I have to admit that this is one of the most obscure parts of Vulkan, which is why you should definitely use some reference code here. Now that we understand how the layout transition takes place, we are back in the record command buffers function, and in the same location where we started the old render pass, we call begin rendering to start the dynamic render. And this of course needs to happen before we record the draw commands into the command buffer, which takes place here. So this function is here below, and everything here should look very familiar. It's basically a replacement for the regular render pass. The function is called vkcmd begin rendering, takes the command buffer, and an address of a rendering info khr structure. This guy defines the render area, which goes from pixel 00 to the window width and height. Layer count is 1. We don't care about the view mask, a single color attachment, and accordingly the address of a single color attachment structure, and a single depth attachment. And these guys are up here. So for the color attachment, we specify the image view, and we have a function to get the image view for this index, for this image index, from the Vulkan core. The layout is color attachment optimal. We don't care about resolving at this point, so resolve mode is none, no resolve image view handle, and of course the layout is undefined for the resolve image. The load operation is load up clear. So before we start actually rendering, we have to clear the color attachment, and the store up is store, because we want to keep the results there. We also have the option to specify a clear value, same as we did with the older render pass. So this guy is here. Next we have the depth attachment, which is very similar. For the image view, we have a different function to get the depth view. Remember that all the views are kept in the Vulkan core, so there is no problem retrieving them by the index. The layout is depth stencil attachment optimal. Same thing for resolving, also clear on load, and store the results. And then for the clear value, we set the depth to 1 and the stencil is 0. And then with all this information in place, we can call vkcmd begin rendering, which is actually a void function, so I'm not checking any return value here. Back to the record command buffers, we bind the pipeline, record the draw commands for this model into the command buffer, and then we call vkcmd end rendering, which is the corresponding call to this function. Then the barrier, and then we end the command buffer. And now everything is ready, so hopefully it will work without any warning. In the terminal, we can see that the Vulkan loader supports version 1.4.304, which is the result of the enumeration of the Vulkan instance version that we've added. Then we have a bunch of prints from the driver. And then when we initialize the device, which is an NVIDIA GTX 1650, we can see that the API version of the device is a bit older. So perhaps I need to update the driver, or maybe they haven't updated the driver yet for the latest version. But we can see in the list of physical device extensions that this device supports dynamic rendering. So there's no problem. The extension is there, the version is okay, and everything is okay. We also have no warnings here, and the dragon seems to be happy. And that's it for today. Thank you for watching, and I will see you next time.